with that, we will start with the first example. That is the analysis of a rigid frame. And this is example 12, I believe, right? Right? Example 12. Okay. So what is the problem? The problem is the one that I think this one we discussed before, where I think that the first part, the sway prevented, I think we talked about this, correct? The first structure, this is on the textbook page 239. You have a hinge structure like this, and the loading condition is this. And I think we did this problem, correct? We solved this one before. Or no? Oh, we saw half of it to show the symmetric and asymmetric buckling, right? So we didn't really solve this problem, but we solved like a similar version to it. So we did something similar to that, and that means I will still solve this problem. Now, in the buckling of this kind of structure, there are possible scenarios because the structure has more redundancies. That means it actually has more degrees of freedom. That also indicates that the failure of the buckling mode includes more possible kinematically admissible deformation profiles. And one approach that you can use in identifying these kinematically admissible deformation profiles is to consider that whether the rigid frames will sway or not. Because for some of the rigid frames, you know that because the joints can take moments, even the rigid frames swayed to the left or to the right, you will still consider stable. And that is also the mode when we consider the seismic behavior of buildings. So how does a building dissipate the ground motion, the energy, kinetic energy transmitted from the ground motion? Is by sideways. That tells us that a structure actually can be stable when it starts swaying back and forth. So in this case, if you assume that there's no sway, that means the deformation profile will always have to be symmetric. Sway or not is measured by whether there will be translational deformation, which is back to the loading P. So in this case, the translational direction is the perpendicular direction to the P. That means whether this building will sway to the right or to the left, that is the sway case. If you assume that there's no sway, so we have two possibilities. One is assume there's no sway, or you can call sway prevented.
We can't see anything.
Disappear again?
Yeah.
I got to figure out why. There's no sign on my computer. Then the other way is sway or with sway. In the first case, we will put an imaginary roller, something like this, because we said there's no sway. That means the deformation can only be symmetric. And your loading is like this. And suppose we use exactly the same definition for all these joints. We're going to call them A, B, C, D as defined on the textbook. So this is A here, B, C, D. As long as we don't get to E, we are still fine. And then you will have to define the length and those the length of the beam and also the height of the columns. Length of the beam from here to here. We're going to call it LB. And the height of the column, we're going to call it LC. And about E and I's, that's just like what we talked about before. They don't have to be the same. The EI for the beams, we call it EIB. The EI for the columns, we're going to call it EIC. So what is our objective here? Our objective is no different from our previous analysis. It's all about finding the critical load. But of course, after this example, we can also find the plastic load. That's a different problem. After introducing the plastic analysis approach. So in the swayed prevented analysis, we will consider there's imaginary roller and we consider the free body diagram if we use the force approach. So the first thing we're going to do is to find out, develop the free body diagram from the assumed kinematically admissible profile. So that assumed kinematically admissible profile will give us something like this. We can assume that this is the original one configuration at the boundary. So how does it deform? Well, you can use either way. And if I use the approach, which is the same as the one defined by the textbook, we're going to assume that this column is going to deform like this. Keep in mind that all the joints should preserve the right angle before and after deformation. And the loading, of course, applies here and here. Now, once we have this, so let's dissect this kinematically admissible deformation profile and find out the direction of these internal actions. We have, due to symmetry, I trust that we're going to analyze half of it and the other half will be identical. So we don't have to analyze the entire one. We just have to analyze half of it. And that means we will only consider half of it. And we only look at one side. So suppose we take the left-hand side, the left to the center line, and perform our analysis. One is going to go like this, and the other goes like this. In terms of the members, they are, this one's A, this is B, and this is B, and this is C. Right? So that's what we have. And of course, let's not forget about the joint. The joint is going to be something like this. And I can move the joint a little bit further so it will not crowd it in this area. So let's move the joint to be here, because we need a joint in order to show the location, the application of axial force P. And from reaction analysis, of course, you know that there must be a reaction P here. Right? Now, directions of, this is the interesting part. Let's find out the direction of internal moments and also shears. Starting with the member without the force P. In this case, look at the member BC, internal moments is going to go this way. Would you agree? So this is the direction of MB. If MB goes this way, the other one must go the other way. If you have MB goes this way, you use MB to find the shear of member AB. So what's the direction for this? In order to balance this MB, the shear force at support A must go horizontally, pointing to the left or to the right.
To the right.
To the right.
To the right. You're right, to the right. So this is VA. Now if VA is right, pointing to the right, VB must be what?
To the left.
Pointing to the left. So this is VB. If VB is pointing to the left, what happens to at the beat end of column AB? What happens to the B end of the member BC?
You have a VB pointing to the right.
Yes, it has to be going to point to the right to pass the force. So this will be the VB here. Okay. Now, with the member BC under the application of MB, what happens to the shear for member BC? You know the shear for member BC, if I use different colors just to distinguish it, because there's too many blue colors signs here. It's gonna go vertical, but it should be pointing to up, or should be upward pointing, or should be downward pointing, up or down?
Up.
Downward?
Should be down, right? Should be down?
Yes. I believe so.
Why should be down?
Because in the joint at B, it's gonna be resisting the force P, so it's gonna be opposite.
In order to resist the member MB, if you look at this one here, we have a moment going this direction, right? And the force in here, this force must balance the application of this moment MB. So which direction of this shear force to member BC? If it goes up, if it goes down, that means it will be going in the same direction of MB because it will produce the same moment. Correct? It will produce a moment in the same direction of MB. Can you see that? Correct? So if it is downward pointing, that means this shear force to the member BC will not be in any way producing any counterbalancing effect to the member MB. So it cannot be downward pointing. It has to be upward pointing in order to balance it. This is just like the way we determine the direction of VA. How do we figure out the direction of VA? Because it has to be against in the opposite direction of MB for member AB. Now the same logic